All right, so this is supposed to be a more relaxing talk seminar. It's slightly out of the context. You will see we are going to be quite far from metal structures and superconductors here. So this research is sponsored by the Hartree Center. They gave us access to BlueGene. It's a very powerful machine. NVIDIA gave us access to GPU technology, which is a graphical processing units. They were quite useful here. And Axeleris is a company which is selling one-step and cast-step. I will explain a bit what they are. So my collaborators, mainly was the main driving force of this project is Mike Payne. He was the head of the Cavendish and resigned his administrative duties, so he has finally some time for research. He's quite happy about that. This work was done with Gabriel Kotlia at Rutgers, Peter Littlewood at Argonne, and David, Nicholas, and Daniel all contributed to run part of the calculation and do the data analysis. All right, so the idea is to try to motivate why we might need some new technology to actually apply DFT plus DMFT to a non-periodic system. Most of the technologies we have today actually applies to periodic systems with a few hundred atoms in a unit cell, and a few hundred atoms is already quite challenging nowadays. I'm interested in strongly correlated systems, as most of the people here. We have seen many examples of transition metal ion based systems, which were either superconductors or had a metal to insulator transition, like in VO2 or V2O3. And there are many, many exciting materials here in this region. What was not covered so far in this conference is whether or not we might build something else than just materials out of these transition metal ions. Actually, transition metal ions are also very important in nanoscopic system, and one type of system we will discuss today is enzymes or molecules which are actually based out of iron, copper, or cobalt. And I will try to motivate today that this transition metal ion also drive a very interesting physics in this system as well, even if they are not superconducting or condo insulator. The standard model of strongly correlated system is the Hubbard model. And this was very nicely introduced and explained in detail by Antoine and many people in the audience. Just to say that one of the breakthroughs in the last decades was that we could combine this type of physics with realistic calculation based on DFT. And the only difference in this talk is actually that I will move from the one Brilliant zone picture, which corresponds to a solid or material, to something which is essentially a gamma approximation where you don't have any periodic structure anymore. There are a few simple examples for that. For example, you could think about nanocrystal or nanoparticles. Another type of very exciting example is iron oxide nanoparticle in principle, in particular, which these nanoparticles are used for cancer treatment and medical imaging. So that's one of the axes of our research. We've been trying to extend our calculation to this particle. Another type of system would be periodic, such as heterostructure, discussed by Andy Mullis this morning, where you also have very large unit cells. So it would be nice if we could derive a methodology which is optimized and quite efficient for very large structures. Just another possible example, for example, self-assembly on metallic surfaces. If you do a deposition of very heavy head atoms on a metallic surface, you can also think of very interesting physics. For example, this is a superlattice of cerium head atoms on a silver surface, which is spontaneously organizing into a two-dimensional ordered superlattice. And finally, of course, enzymes or molecules, especially metalloporphyrin systems. So this is what I will discuss today, actually. So these are just a few examples from the top of my head. I'm sure you could come up with many different examples as well. What they have in common is essentially that you need to solve systems which have something like 2,000 to 20,000 atoms in the unit cells if you want to retrieve realistic and interesting systems, which nowadays is still very challenging, even if we have supercomputers. DFT codes have been optimized a lot. I mean, this still remains something which is quite in the challenging side. I will skip the DMFT explanation because you're now all experts in DMFT. Well, the idea of DMFT, maybe in the context of molecules, is that you will have a very big system. Think of it as, for example, an enzyme or molecule. In this molecule, you will have a very few correlated centers, for example, iron or copper. And the idea of DMFT is, as it was very well explained in details, is to treat in a very detailed way the correlated centers and use a self-consistent procedure to map back the Anderson impurity model physics back to the full system. So in a molecule, the difference is that you really will have physically only a few correlated centers. They might be quite far from each other or quite close. This will depend on the geometry of your molecule. But then the DMFT is even more justified because in this type of system, the physics is going to be very local. The pitfall or the catch is that essentially now we have to write the DMFT equation in real space. So there was quite some activity about that in the last decade. Essentially, we can write the Dyson equation in real space as well. The difference is that now you will have a very big matrix. Each site will correspond to an atom or orbital of your system. And you will have to write the self-energy or compute the self-energy now for each of the sites of your molecular lattice, at least for each of the correlated sites. So that matrix can be as big as the number of orbitals in your system. So if you have 20,000 atoms, you might end up with 100K or even larger matrices. So we can already see what the problem is here, is that we'll have to invert. There is an inverse here. So we'll have to invert this big matrix, and we will need to find some very efficient algorithm to do that. So that can be quite challenging, and I will have a short discussion about that. But essentially, you have the formalism to have DMFT in real space in connection with DFT. So there are quite some very professional, very optimized DFT plus DMFT packages. You have a list here. I mean, Win2K plus Trix essentially will be taught by Michel and Marcus in detail next week. There are quite a few of them. So what we tried to do recently was to derive one more package, but in this gamma approximation. So we have to use a localized basis set because essentially most of the physics will be local. It should be in real space. It should be able to tackle large unit cells. And as I will explain, the catch is that essentially the price that you have to pay is that your orbital won't be orthogonal. And that can be quite a headache for DMFT. And I will go back to that in a minute. So a breakthrough in the last 2 decades about how you can apply DFT to very big unit cells in real space is called linear scaling DFT, or big DFT as well. The idea is that you will write density kernel in real space, and you could start, for example, by using your usual set of molecular orbitals, and these orbitals will be quite delocalized in your system. The idea is that if you can write this in terms of much more localized orbitals, such that they really only see each other very near-sighted bonds, well, in principle, if you have density kernel for the full system, you could in principle neglect interaction between that site and that site if these two sites are very far in space and if your set of functions are very localized. This is called the density kernel truncation, and that's an approximation, of course. It's a good approximation if your system is quite localized, such as in an insulator, in a molecule, or for a system which is at least near a metal to insulator transition. So that's an approximation, but if you do that, what you win is that essentially the time that you spend to solve the full system will scale linearly with the size of your system because you only have to solve exactly what happens within some sphere of radius r around one of the orbital, and you can just neglect our interaction. So this is what was called linear scaling density. And one implementation of that is called the one-type code, developed in Cambridge by Mike Payne. And essentially, you have one example here, how the time spent solving a system which contains a few thousand atoms scales with the usual DFT code. So it goes like n cubed, where n is the number of elements in your unit cells, when compared to linear scaling DFT code, which scales completely linearly up to a size of 6,000 atoms. So the time that you win actually for linear scaling density code is such that actually is mainly the only way to really access very, very large structures. So it seems to be a very powerful tool. It has quite a lot of catches and problems as well, of course. but at least it seems to be well suited to describe molecules using localized bases. So how does it work? Well, it's essentially optimizing both the basis set in real space and the density kernel. And the basis set, this set of functions that are used to describe molecules, are written in terms of a support basis, which is a grid, which contains very spiked functions. And essentially, you are changing the coefficient of your basis set in terms of this support basis. And at the end of the day, you will both obtain the Kohn-Sham basis and the density kernel in an optimized basis set such that the energy is minimal. There are quite a few parameters to adjust, which will control how exact this procedure is. One of them is the truncation of the density kernel, as I discussed. The other one is actually the radius around one atom, up to which you will actually allow this coefficient to be non-zero. So you will optimize your basis set, but only assuming that your basis set, your functions, stay finite only in some sphere of radius r. And of course, the larger this sphere is, the more precise your calculations are. So I won't go too much into the details, but this gives you an idea of the approximation involved in this procedure. And what we did recently is to combine this type of DFT approximation with DMFT. So we essentially start by writing the Green's function. So this set of this basis set that you obtain is essentially non-orthogonal. So you have this overlap matrix S, which comes into the game. I won't go into the detail of the equation, but essentially you will see that at some point you obtain an Anderson impurity model, and which also has some projected overlap matrix. Your atomic set of orbitals for the Anderson impurity model, your d orbital, are orthogonal. Nonetheless, you will find that because your original system was non-orthogonal, you still have some reminiscence of that, and that appears in this overlap matrix O. So you will have to take care of that when you do the DMFT. But essentially, everything is well defined, and you can do it. And I will like now to introduce one possible application of that, which is skip a few things, which is myoglobin. So why myoglobin? Because essentially this was studied really in details for more than 30 years. And after 30 years, there are still open questions. And there is a very simple open question, which is that if you do the simple DFT calculation for this simple molecule, you would find that myoglobin binds to carbon monoxide 20,000 times more than it would bind to oxygen dimers. Just as a simple reminder, myoglobin and hemoglobin are both responsible to transport oxygen 2 in your bloodstream, essentially as part of our respiration process. If that would be true, if myoglobin would always bind only to carbon monoxide, it would mean essentially that it would lead to asphyxiation, essentially. We wouldn't be able to breathe, and that would be a big problem, so we will all be sick, or worst case scenario, dead. So that cannot be true. So the result obtained by DFT is really striking and asks for clarification. So the question we can ask is, what is going wrong here? Why is it that we can't explain something as simple as the binding of the simplest possible molecule to oxygen 2 or carbon monoxide? There are two possible scenarios that we suggested. One was the effect of the protein, so the fact that the protein could have different conformation. The other one is strong correlation, and I will now go to this second scenario. And the idea is, can we understand how the strong correlation present at the iron site, which is binding to oxygen 2 and carbon monoxide, could affect or change the binding energies of this simple molecule. And before going to the full molecule, I will focus on the kernel of this molecule, which is very small. The kernel of hemoglobin or myoglobin is called heme. It's a very small molecule. You have the iron site here. This is called the histidine center. Essentially, this molecule is unligated here, doesn't bind. And here you have the version where it's binding to oxygen 2. And the first thing we did is we did the DFT plus U calculation. And we checked if by increasing U, you could reduce the difference of binding energies. So this is what you see on this graphic here. And by increasing U, you have here the binding energy of oxygen 2 and carbon monoxide. You see that the binding energy of carbon monoxide is always much lower than oxygen 2. As you increase U, things get better. But it seems that if you go to a very large U of 8 electron volts, you will essentially find that these two molecules finally have the same binding energies, so at least things are improving. However, that's much larger than the value you would estimate by constraint RPA, which is much closer to 4 electron volt. Also, you would find that you have 7 electrons on iron, so you would have a very poor charge transfer, which is not what experimentalists would agree on, so that's also quite striking. And if you look at the spin, you would find that this is nearly fully polarized. So when you increase U, DFT plus U tends to build a very strong polarization, which is not very realistic for such a small molecule, essentially because you don't expect this to be a very strong magnet, so something is quite strong. You would expect a fluctuating moment instead. So can we do something better than DFT plus U? Could we recorrect and solve this problem? Well, DMFT is quite good. And for which reason? Well, DMFT will know about quantum and thermal fluctuations. It will involve multi-determinantal effects, which are not present in the DFT level, which is a ground state approach. You can describe a fluctuating magnetic moment easily. It will maybe correct the ligand energetics, hopefully. And it's a method which goes beyond just energy level crossings, because you have this hybridization between the iron atom and the rest of the molecule. So let's see what DMFT can do. Just to emphasize that even for this simple heme molecule, you have 240 orbitals, so that's already beyond what you could tackle the brute force approach. So DMFT is quite well suited for that, because it's actually quite a precise description of an Anderson impurity model, where you have a correlated center here on impurity connected to a bath or to a surrounding environment. And we can use simple mapping from that to this Anderson impurity problem, compute the self-energy, go back to the full molecule, and look at the energetics. So that's what we did, and I will show a few results about that. How much time do I have? Perfect. So the first thing that we can look at is to think about what could be missing in the DFT description. And just to go back to the DFT plus U calculation, what is obviously missing here is the Hund coupling. And if you ask to a physicist what would polarize the iron state, he would directly tell you, well, probably the Hund coupling is very important for that. The Hund coupling will build a spin, and for a very strong, large Hund coupling, you will start to build up magnetization. And that was completely neglected in all the past 30 years of calculation on heme and myoglobin. So here on this plot, you see the density of the iron atom as you introduce in the calculation the J Hund coupling, which is on the horizontal scale. And this just shows what, at least it tries to answer the question, what happens, or does anything happen as you increase the Hund coupling in this heme molecule? And this is new, and people didn't look at that. And what people would have expected, coming from the DFT plus U calculation, is that the J does not do much, because J is much smaller than U. As you can see on this plot, the density of your iron center for different configurations, so this corresponds to heme, which is unligated or binding to O2 or CO. In any case, they all have the same trend, but the density when J gets larger than 0.5 is drastically affected and goes down and goes to the value of 5. So the first thing we can see here is that essentially, yes, the Hund coupling does something. It has a very drastic effect on the iron charge. And for any estimation you would get from constraint RPA for iron in this type of system, you would find anything between 0.5 and 1. So in the physical region, you can see that you have a sharp drop of the density of the iron and the U correlations. And you could do, so yeah?
Why the DFT plus U doesn't have J? Would it have J?
They didn't include it in it.
But what if you did? Would it be different from this?
That's what we're trying to do now, to see what is the impact at the mean field level of J. Okay. So the simplest, I agree, the simplest possible question you could ask, what happens if you include J? It turns out they didn't try it yet. So yeah, I completely agree. And actually, to go back to this question, to answer what would happen to DFT plus U plus J, I think it wouldn't be too bad, because what happens essentially, I'll go back to this point. I think it explains what's different between O2 and CO. And at least something happens, and it's something which seems to be important. What you can see here is that also, maybe I will show it on the next slide. When you include J, if you look at the charge of the highest occupied orbital, in a molecule you will always find a gap. And you can look at what is the symmetry or charge distribution in the highest occupied orbital, which is below that gap. When J is 0, the charge is pretty much delocalized and present everywhere in the molecule. When you include J, you see that the charge is quite pinned around the iron center. And essentially, you see that you also have a kind of a symmetry selection, where essentially the dizzy orbital is mostly dominant in this highest occupied orbital. One more thing that you can see is that the charge is transformed from the iron atom. There's this reduction of the charge, and the charge goes somewhere. So the question you can ask is, where is this charge going? In this IM group, you have actually oxygen electronegative groups, which are called the hydroxyl group on these two sides. Actually, we found that actually the charge is simply transferred from the iron atom to both of the hydroxyl groups. So essentially, there is a charge reduction. The charge goes to the border of the molecule, and you have a change of orbital character. All of that's driven by J. So at least something happens. It's quite interesting. In terms of physics, what could that mean? Well, it's interesting to see that in this highest occupied orbital, the charge density is mostly around the iron center, which means that if you think in terms of docking a ligand to this molecule, well, the charge is only present here. So if you want to have some charge transfer, your ligand has most probability to bind to the iron. There's nowhere else to go, essentially. So that was one interesting result. The only thing we can ask is how far the DFT picture is valid. In terms of DFT picture, people were drawing cartoon saying that the iron was mostly in configuration of doublets and spins. So you can ask the question if you can redraw a cartoon or not to describe what is a spin state of iron. So what you can do is look at the quantum entanglement when you draw your resonance matrix of the iron, and you trace out the bath degrees of freedom. And you would obtain what is called the reduced density matrix, and you can compute the eigenvector of that and look at the von Neumann entropy. So the von Neumann entropy of this iron atom just tells you how classic you are, if you can just have a classic cartoon picture of the iron atom, or if you have something more complicated. And we can look at what happens here for the entropy. And again, if you look at the entropy when you increase the Hund's coupling J, you see that it's not that large when you start with J equals 0, but as you increase J and you go to the physical regime, there's quite a sharp increase. And you can look at the cartoon configuration, and since you have now DMFT, you have a superposition of different states. So for J equals 0, you have a superposition of a few states, dominant state, which are mainly the doublet state and one polarized state. But as J goes to 0.8, you see that the number of states just increase a lot. And you really cannot speak of, you cannot really pin any dominant configuration here and say that for this molecule, the iron atom would be a cartoon picture where you just have one particular spin state. So we found that actually here you would find strong spin and charge fluctuation, which is a bit against the canonical picture of how you would, if you would talk to a chemist, this is not what they had really in mind, actually. So that's another interesting thing. So far, it was really a toy model, just to see what new things we could bring with DMFT. We didn't solve anything yet, and now we want to go one step further and really answer a few quantitative questions. To do that, we moved to myoglobin, which is a full molecule, not only the small kernel, with 53 residue, which is actually something we can compare with experiments. So that's now the full molecule. So again, the problem is that there was this one electron volt difference in the binding energies between O2 and CO for this molecule. And we try to answer this question by including both U and J at the DMFT level and see if we can explain what happens. So here, the first thing we found is that if you look now at the charge of the iron atom as a function of J, the same thing as I showed before, for both myoglobin O2 and CO, you found that now, if you include the full molecule, there is a different response of the system. So myoglobin O2 has a quite, as soon as you tune on J, there is an increase of the charge of the iron atom. In myoglobin CO, actually, it's very flat. So the myoglobin CO is very unresponsive against the Hund coupling. The reason why is that when you have the full molecule in the right physics, you have a very strong covalent bond between the CO dimer and the iron center. And this strong covalent bond brings really the iron levels down in energy a lot. So you need really a very large Hund coupling to start to see any effect. In myoglobin O2, the levels are much closer to the chemical potential. And essentially, as soon as you start to put on the Hund coupling, you build up a magnetic moment or fluctuating magnetic moment. You bring the states down in energy closer to the Fermi level, and you see a response of the system for quite reasonable J value. So there is what we call a discrimination effect between the binding to O2 or CO. So the two systems seem to be quite different. And now to go back to the question of Andy about how DFT plus U plus J would compare to that, I think it wouldn't be that much different because this effect of bringing back the states closer to the Fermi level is essentially a mean field effect. Well, sorry, yes? Yeah, perfect. So where the DMFT might do something else is when you look at quantitative numbers such as the energy. When you look at the total energy of the system, and we have seen that we have strong valence and spin fluctuations, essentially there you really want to capture all the possible effects. And also you want to work at room temperature. Again, hemoglobin is not a compound that is in our bloodstream at 0 temperature, but it's at room temperature. So all these effects can actually correct the energetics. What we found is that if you look at the binding energy of CO, which is the blue one, and on O2, which is the red one, essentially they cross around J equals 0.7. And again, we are not discussing the exact value of J. You could argue on what you would obtain by constant RPA within some error bars, but at least this is a very reasonable value for an iron atom screened by nitrogen. So in our view, actually, this is the physical regime where at least it is reasonable to think that the two molecules now have the same binding energy. And to convince ourselves of that, we can do some comparison with experiments. We have access to quite a few experiments. One of them is single crystals of myoglobin extracted from sperm whale, where essentially you have on the right side the DMFT optic spectra compared to the experiments. One striking effect was that in experiments in the infrared regime, they saw that there was a peak in the O2 spectra, which was absent from the CO spectra, which is also reproduced in our calculation. And people made some suggestion of what that could be, and they assumed that it might be a charge transfer from the iron atom to the oxygen 2 dimer, and which actually is exactly what we found in our calculation. So now this is not only an assumption or a theory, it's something you can really extract from the calculation and tell the experimentalist, yeah, this is what is going on. All the other features, like this is an iron to nitrogen transfer, and this is the third band, they all correspond very closely to experiments. So it's quite convincing, I think. And just maybe in the last minute, one thing that we can do with this one-tap package is that we have access also to all the chemistry packages. And chemists are very good at writing orbitals. The problem in DFT is that you cannot really trust anything which comes from the quantum orbitals individually. You can only trust the trace. But here, what they do is that they can transform the quantum orbitals to a language which corresponds to the bonding orbital. So if you have a carbon-nitrogen, that would be a bond, or you would have the antibond here. And you can do this you can use that as a new basis, which is physical and justified by chemistry, and see what happens. And that's a very powerful tool because you can really know and see what's going on. for example, here, the binding between iron and the oxygen 2 dimer in this basis shows clearly that you are binding a charge which is combining the iron and the histidine nitrogen atom here to the oxygen dimer. And that's a very close, very powerful resolution. You can really tell what charge is binding to which one. And this kind of information can be compared to LH XAS. And one of the big problems they had is that in LH XAS, the pi character, the pi hole character, was found to be quite low, about 15%. And if you compare the best estimate obtained by quantum chemistry packages based on CI, they had a much larger value, and this was a big discrepancy. If you compare to what you obtain with the DMFT, that's much closer. So at least we have it seems that when we compare one by one, the different methods, DMFT is not too bad. It's quite in a good shape. And we actually explain, we give a reason why that would be the case, and we'll see by discussing with chemists how this is accepted. So this is my conclusion. I hope I convinced you that with DMFT we can bring some insights into quantum chemistry, that we can have some reasonable agreements with available experiments, and that's not so hard to do. There could be a lot of interesting things that could be obtained with similar methods. So thank you for your attention.
Thank you. We have time for a few questions, comments.
Yeah. For the quantum chemistry calculations, you can actually use Boyce localization function instead of Warnier DFT in Boyce localization. So did you compare how the results are with the Boyce localization?
How they depend on the choice of functions of molecular orbitals.
Not molecular, localized molecular orbitals.
Well, the function we use actually in our package are very close to the Vanier functions.
Okay.
In principle, if our cutoffs, if the sphere around an atom would go to infinity, we would find back exactly Vanier functions. So if you want, the fact that you don't have Vanier functions comes from the fact that we are using some cutoff approximation.
Mm-hmm.
In principle, I think all these results would be very similar to a Vanier basis in principle.
Okay. And did you also use relativistic calculations for some of any other atoms heavier than iron or something?
If we compare to other chemistry packages like Gaussian, for example. That's one of the things we are doing now. So we started to compare with CAS-STF, which is essentially, exactly, which is one of the state-of-the-art package you could use. Well, at least as I was told by my friend chemist. Now, more comparison could be done, definitely. I mean, we are still in the state of comparing experiments and what we have.
Because the number of atoms that you showed today, we can handle in DFT.
Yes.
Quite easily in some localized bases. And
yeah, that's true. So for myoglobin, which is 1,000 atom, that's still in the range of things you could definitely do with DFT or with QM, for example. The reason actually why we focus on myoglobin first is actually exactly for that reason. We really want to compare with other methods, see what we could do, see if it's reasonable or not. Yeah, absolutely.
So these are, of course, definitely all insulating. How big is the HOMO-LUMO gap?
For this about 0.5 electron volt in this well, actually it will depend if it's binding to O2 or CO, but it's about that scale, yes.
No, I'm just wondering how important is your dynamical fluctuation, because you are doing a DMFT. I think he asked already the question.
So,
if you have a
static
description of LD plus U.
Yeah, so we are definitely not in the regime of a very strong multi-insulator.
Yeah.
So essentially everything is always not so far from the Fermi level or from the chemical potential. The point is also that as the molecule is bigger, you will always bring more and more states around the chemical potential. That's typically what happens.
That's like half electron volt.
In that case, yeah, it's about half an electron volt. And for the
Sorry, just a very quick question. Why do you keep saying DMFT? There's just one correlated site. This is just an Anderson impurity model, right?
So you're absolutely right. It's not in the spirit of cheating you, not at all. The first thing is that this, as it is is completely, you can generalize it to any system which has more than one center, and of course then you have DMFT. The other reason is that for quite a while we are looking at how the spin on iron would affect the spin on the oxygen. In that case, you can do, for example, you can use single-side DMFT on each, which is an approximation. Then you really get some kind of DMFT where you have to iterate the full procedure. So depending on what exactly you do, this can be or not called DMFT. In that case, everything is exact. There is no mean field because you have only one correlated atom, so there is no approximation involved there. But you're right, yeah.
Okay. Please join me in thanking Cedric once again.